Welcome everybody to today's FDTD Go 16 Applications webinar. Today we're pleased to have Bob LaPlante and Zach Zefkovich from the Weather Service office in Cleveland, Ohio. And Bob will be leading our presentation today, which is covering the Erie, Pennsylvania lake effect snow event from December of last year. So let's go to the next slide. Just a few things to go over before we get into our presentation. All of these presentations are recorded and they will be available on the visit web pages at the URL that you see here, so you can view these at any time. We'll also have a Q&A at the end in case there's any specific questions on GOES. Also, we're looking for future presenters, so if you're interested in leading one of these in the future, just let myself, Dan Bicus, or Scott Lindstrom know. Next slide. We'll have about 20 minutes for our speaker for today. You can either send questions via the GoTo chat, or at the end we'll have a Q&A period over the phone. It will be done by 18:30. Please remember, do not press hold. And also remember to mute when you're not speaking. So at this point, I'll turn it over to Bob.
Okay, thank you. Well, let me begin here. We had a historic snow in Erie, Pennsylvania last Christmas, and we're going to be showcasing that, I guess, with this session. For the agenda for the talk, I'll give a brief meteorological synopsis of the event near Erie, PA. Highlight a feature we've had since the dawn of the 88D era. That is, we have a radar coverage gap near the city of Erie, and we're trying to assess and hope that the GO 16 imagery will help supplement the radar observations there. We'll also explore some of the additional features of GO 16, the base channels, the RGBs, and some of the other products like the split difference product during the event to see how these other products, the properties that we can glean from them, can help us deal with the surface conditions. And we'll also give a brief summary of the snowfall that did occur in Erie during this 24-hour period that we're going to speak about. For lake effect snow, I know not everyone may be overly familiar with the mechanisms that produce it, but this is just a very brief focus for the city of Erie. For the first half of the, for an optimal situation, we would like to have the water temperatures warmer than average, just so there's more buoyancy and water vapor available for lake effect snow production. And the first part of the season, there's little or no ice coverage on the lake, which also increases the fetch length and the ability of the air to absorb heat and moisture. So, in addition, another factor we consider is the band shape or formation, a single-banded form with a fetch coming in with a wind direction from about 250 to 260 allows a 200-mile fetch across the lake that then intersects the south shore of the lake near Erie, PA. That's the optimal, or the worst case, depending your frame of mind, for snowfall there. And you often have convergence in the boundary layer with the band. The band kind of drives the whole overall mesoscale circulation in and near the lake. And we'll have southwest flow on the American side and northwest flow on the Canadian side with strong convergence therein with upward motion, and then divergence aloft. So you have a circulation center. You preferably don't want much in the way of wind shear. You want unidirectional flow. And you want a deep boundary layer. Typically with these intense events, they're greater than 10,000 feet high, maybe 15, even 20,000 feet. And it would be nice if there's an upper level system nearby, so you have maybe cloud seeding from above and an overall more moist situation. And that scenario also deepens the boundary layer. This was a sounding from Buffalo on Christmas morning. You have an inversion, the base all the way up to near 500 millibars, so this is a very deep layer, sufficient for very intense lake effect snow. And this is a buff kit sounding centered for the city of Erie off the NAM model, which does show really a very deep mixed layer, unidirectional flow out of the west to perhaps northwest, around 35 knots or so. And Looking at the synoptic features, we had a system come up through Ohio and went up to about Watertown, New York at this point. And you see the flow over the lake is southwesterly in here and then northwest in here. So a band basically generally formed down through that long fetch. Later in the day, around 18Z, that surface flow is pretty much long gone, and there's west to southwest flow across the lake. And similar situation by 0Z 6 hours later, with a little more convergence in the boundary layer than previously. And 6Z, really no change, still a lot of convergence heading in toward Erie, and a little bit less by 12Z. Now this is a visible loop here. Unfortunately, I didn't put the exact times, but obviously it's visible, so we know it's daylight. It's probably somewhere between 14 and 18 Zulu on Christmas Day, showing just the overall activity on the lakes. I wanted you all to get a feel. We have a fairly intense band here going into the Tug Hill of upstate New York, and we have some multi-banded structure here in Erie with maybe converging into a primary band there, and then some multi-bands here up on Lake Ontario. Now the next loop, I zoomed in a little bit. Let's see. I'm wondering what just happened. Is your screen?
Yeah, I just see white.
Let's see here. Let me see. Let me try this again. Yes, okay. Well, let's see. I'm trying. Some of those loops didn't load fully.
Bob,
all right. Well,
we could use it from my end here if you'd like.
Okay, why don't you try that? So let's go back to the second loop, which has the divergence. The labeling is the divergence of the LES band, cloud top.
Slide 14.
Yeah, do that. Do I need to give you control?
Let me see, I have it on my screen too if you want to.
Okay, do you see my screen, Bob?
No. Let me. Okay, we can see it now. Okay, so what I was trying to show here, if you look closely at the tops here, near Erie PA, you'll see the divergence of the cloud top in the animation. That's the point I wanted to get across here. So if you go to the next slide. I've added on the reflectivity from Buffalo and Erie, Buffalo and Cleveland's WSR 88D. Now, at this point during the day, the inversion height was extremely high, upwards of 500 millibars. So the bands were fairly intense, and there wasn't much in the way of a radar coverage gap over Erie PA at this point because the intensity of the band was such that the radar network was able to survey it adequately. Now, if we go to the next slide. Okay, I wanted to look at other additional GOATS products that are available now, and this was the day cloud phase distinction RGB, and with the associated key from the quick guide that's describing it. Now, in the literature there basically said the glaciated lake effect bands are associated with heavy snow events, and this time of year with the low sun angle and the overall cold atmosphere, which the lake effect is developing and really gives it a reddish sheen to everything, and so we don't really have the bright yellow cloud tops. There's some suggestion there on the south side of all the lake effect bands, whether they're coming off of Michigan or Erie or Ontario, that it's it's saying thick, high-level clouds with ice particles. So, you can get that sense of it there. And then there's some lavender or purplish colors at basically at the beginning of the lake effect band formation areas off of Lake Michigan especially, and over the western edge of the Erie band as well. So those are probably the lower clouds that are more water vapor, liquid water. Okay, if we can go to the next slide. And this is just the sounding at Buffalo by 0Z 12 hours after the earlier ray ob there. And we see the inversion has now lowered down to about 650 millibars. So the overall inversion base is lowering, so the depth in which the lake effect can be produced is decreasing, but it's still substantially high. It's still intense, but it wasn't sort of extreme as it was earlier during the daytime hours. So if we go to the next slide. And this is the buff kit sounding at that point, too, which shows the inversion roughly around 10,000 feet there at Erie. Okay, the next one. This is model-derived, obviously, not the ray-obs. That's why I'm trying to show both of those. And then by 6Z, it's dropped a little bit more. Very unidirectional flow you can see there with the wind indicator there in buff kit, for those that are familiar with that. Next slide. And here's the 12Z sounding with the inversion lowering substantially more. Still westerly flow. Now we're down to about 750 millibars. All right, so then the next slide. So what we have here is the channel 13 infrared imagery, and basically in the middle of the night, somewhere around 6Z, 3 to 6Z, showing you the single primary band coming just north of the islands in the western basin of Lake Erie, and then eastward, and then intersecting the shoreline in and near Erie. Meanwhile, there's also another intense band up in hitting the Tug Hill in New York. So it's a pretty active night. We can go to the next slide. This is just a zoomed-in image there, and I don't know if you can make out the surface observations. I think my yellow doesn't quite cut it for me here, but there's heavy snow in Erie, and they had several hours to many hours overnight of a quarter-mile less visibility and S+ heavy snow. Okay, so we can go on. Next slide. And what I've added on here is the Buffalo WSR 88D, just showing you the coverage limitation, and it looks as though they can track the band's intensity into southwest New York, but by the time you get down to Erie or Prescott, which is that little small peninsula sticking out into Lake Erie there, the reflectivity is subpar. You're overshooting by then for the most part. Now if we go to the next slide, we'll see the contribution to the radar network from Cleveland's, and there again, the band is pretty intense north of Cleveland, but by the time you get up near Erie, you're pretty much overshooting things. And this is a fairly intense band here in the middle of the night. So if we go to the next slide, we'll see the two radars together. And so there really is not much in the way of reflectivity over the Erie region, somewhere around 10 dBz returns. So that's basically what I'm trying to highlight here. So we've been dealing with this problem for 25 years or so there. So if we go on to the next slide. We want to at this point look at some of the other imagery, the RGBs, the split cloud phase products, to determine any relationship between the cloud top properties and the intensity of the radar reflectivity and surface snow observations. So if we go on. Now this is the nighttime microphysics, which seems to be a very useful product for many applications, certainly not just lake effect, but fog and precip type, and I think it's probably one of the best nighttime products there is for the RGBs. And so here I think the cold scene in the winter time it's making it a little difficult to exactly consult which part of the legend we should be looking at here. What we see is in number 10, the high, thick, very cold clouds are kind of yellow-green and noisy is actually the end phase or the end result of the lake effect after the clouds have moved inland from the lakes and they're somewhat glaciated with not much in the way of snowfall underneath, at least for the most part. You can see that especially maybe up in upstate New York. There is some of that in southwest New York off of Lake Erie. And then in the initial part of the bands, it's more of this brownish, yellowish color with thick high water and or ice clouds. If we go to the next slide, we'll start adding in the radar data. And what I wanted to try to get an idea of, is there any relationship with that derived cloud top with the radar reflectivity? And it's a bit of a challenge to really interpret everything. So that you can, on your own, I suppose you could go back and forth between the two product types here. And go to the next slide. Okay, and I want to introduce this other product here called the split cloud phase. And it's we're looking at brightness temperature differences. And if you look at the key down below, what we're looking at is obviously a lot of values near zero, where the magenta colors, the brighter the magenta, the more negative the value. And if you look at the key there, that would mean large negative values would have small ice crystals in them, and smaller negative values would have larger ice crystals. And by the time you get positive values, which on the scale there are more bluish, you're into liquid water droplets. So the question is, can we use this product to associate this product with the radar reflectivity? Do we have areas where we have large ice crystals at the top? Are we getting more higher snowfall rates, or do we get higher snowfall rates when we have more liquid water, or do we even get a lot of grauple when we have liquid water clouds? These are just some of the questions I have. I don't really know what all the answers are, though. But what we see here, in this, just inland of the city of Erie and then into southwest New York, I probably should have highlighted Chautauqua County, but that's the southwestmost county in New York. The southern part of there is, you've got the cursor in there, those values there have gone, they're bluish, which means that there may be, hard to say, water droplets, or the values are actually right around zero, so it's hard to say. If we go forward another screen, what I'm trying to highlight here, go back to the other area again for one second. What I want to show you here is there's this magenta color all over Lake Erie, or most of Lake Erie, but we don't have clouds everywhere. So we have to consult other products, go forward again, and look at this infrared image that's going to show you that it's basically clear over the northern third of Lake Erie. And so you really need multi-products to properly interpret everything we're looking at here. So we have clouds over the central part of Lake Erie, and then the southern areas down near Cleveland, it's fairly clear, and then east of, on the Canadian side, it's mostly clear. So now if we'll go forward, and this 4-panel, I'm trying to interpret what we're looking at more fully. And we have the infrared image up in the upper right with the surface observations there, and then we have the microphysics RGB in the lower right, and then we just have the split cloud phase in the upper left, and then we have the radar with that in the lower left. And we're just trying to, put all these products together to try to understand what are the significance of the cloud top properties in relation to the snowfall and to the radar reflectivity. And it's still kind of a challenge. In southwest New York, you have pretty high reflectivity, but the cloud top phase is different there than over the area of Lake Erie, where Cleveland is showing heavier snow. You have mostly yellow in the RGBs, and yet in southwest New York, you don't. So I'm not sure how to explain that difference. So I guess, let's go forward. Okay, and here's another product that we have is the cloud phase product, where I'm not sure the exact derivation of this, but let this animate a little bit here. But there again, I think one has to be careful with this interpretation too, because it's got a lot of red on there that isn't necessarily cloudy. We could have some clear areas, as we know, over Lake Erie. So I think this product probably needs further refinement. But I just wanted to let you all know that this is one of the products that are available. If we go on, here's some of the observations, some nice shots here. The fellow, from what I know in the how tall was that guy? 5'10"? The fellow was 5'10", so it gets you an idea how much snow fell there without a ruler or yardstick or meter stick or several of them. And then what did we say? That was a Mazda 6 here that was covered over here in the right photo. And if we go forward again, this is the daytime accumulation over near the airport, which is highlighted in the yellow oval. Or a foot of snow, just over a foot of snow. There's extreme variability in that county, you can see, ranging from half a foot to 16 inches near the city of Erie, 18 inches a little further east, and then basically a little more than a trace in the southern edge of the county. And then if we go forward for the overnight snowfall, now we're up to somewhere around 20 inches or so around Erie to nothing in the south. So pretty extreme gradient there. Let's go forward. Now there is a little bit of hope, at least on the radar angle of this. The WSR 88D in Buffalo this winter, the lowest slice has been reduced down to 0.3 degrees. And consequently, that has lowered the beam over Erie County on the order of about 1,300 feet. So that is helping us in Buffalo with surveillance of lake effect and certainly other things. Let's go forward. So in summary, the higher temporal and spatial resolution of the GOES imagery has helped fill the radar gap near Erie and allows for more continuous monitoring at any location. Definitely much better than the previous era when we would get an image every but usually every 15 minutes, and there again the images were old, so they weren't very useful for continuous monitoring. Now, of course, the satellite the imagery is coming in more often than the 88D, so it's surpassed it. But we still need to have more study on all the different properties that we're able to look at now with the new GOES imagery and see how that correlates to snowfall and rainfall rates, perhaps. I'll leave it at that.
Okay, any questions for Bob?
I have one, but unfortunately it's a radar question. Has Cleveland opted to have a lower slice?
Yes, we'd really like a lower slice, and we have been offered, I suppose, to drop our beam down to 0.4. We have a nearby observatory at one of the local colleges that's like 3 miles from the RDA, and we can't go down to 0.3.
They don't want to be irradiated or something?
Yeah, it's going to disrupt their day. So we're disappointed, and unfortunately, maybe even a more tricky thing than that, we may have to choose between having 0.4 or 0.5. We may not be allowed to have both.
Okay.
So we're complicated.
I have a couple comments. That larger scale view that you showed, it just showed the mixed phase of the clouds, but one thing it did show nicely was the upstream influence of Lake Michigan. It looks like you had more moist and warmer boundary layer that you could trace across lower Michigan all the way into the Lake Erie snowband.
Yeah, I believe that's true. I probably should have highlighted that.
Yeah, and the other thing, when you're looking at the nighttime microphysics, you said how some of that was noisy at times, and that's because the 3.9 channel is part of the nighttime microphysics RGB. So when you get really cold there, you'll start to experience the noise there, and it means less when you have that much more noise at the really cold cloud tops.
Okay. Yeah, I noticed downstream of the lakes, you could see that mottled effect, but over, I believe, north of Lake Erie in far southwest Ontario, the peninsula there, it's colder. The surface temps are lower, and when you animate, it almost looks the same as the ice clouds east of Lake Erie, east of Ontario. Just because maybe it's colder still there.
Mm-hmm. Any other questions or comments for Bob? Okay,
and I'll say Brian Mata is not on, so I will ask, does anyone have any general GO 16 or 17 questions? Hearing none.
Okay, well, thanks everybody, and have a great day.